Hello, today I will be presenting our paper, Reasoning Affordances with Tables and Bar Charts. We can't talk about reasoning with data without experiencing it firsthand. I'm going to show you some data and ask you a really difficult question. Okay, here goes. This bar chart shows the test result of a skin cream for treating rashes. The y-axis shows the number of patients involved in the test. The darker gray represents the people whose rash got worse, and the lighter gray represents the people whose rash got better. You can see how they are distributed for patients who did use the skin cream on the left and for patients who did not use the skin cream on the right. Your task is to solve this question. Is the skin cream an effective treatment for rashes? Let's think about that for 30 seconds. To keep you engaged, I won't reveal the answer just yet. And I recognize that this is a hard problem, and I have statistics to back it up. When we showed people this question, about 36% of them answered correctly. So the pressure is off. Don't worry if you don't guess the right answer. Why did this happen? We were curious why people were so bad at answering this kind of question. We looked under the hood to understand why the accuracy rate is so low. We discovered several strategies people used and then led to different answers. Let's walk through these strategies to give you a sense of how people reasoned through this problem. You could have noticed that among the people whose rash got better, more of them did use the skin cream than not. This leads you to conclude that the skin cream is indeed effective at treating rashes. We'll refer to this strategy as the larger strategy. Maybe some of you used that strategy to solve this problem. But that is not the only strategy people can use. Alternatively, you could have noticed that there are so many people whose rash got worse after using the skin cream, and conclude that the skin cream is ineffective. We refer to this strategy as the biggest strategy. You could also compare the difference between the number of people whose rash got worse to the number of people whose rash got better. You notice that more people got worse rashes if they did use the skin cream. We refer to this as the delta strategy. And finally, you could have computed the ratio between the number of people whose rash got worse and the number of people whose rash got better for people who did use the skin cream and for people who did not use the skin cream. And notice that among the people who did use the skin cream, 1 in 3 got better. Among the people who did not, 1 in 5 got better. So there is a higher ratio of people whose rash got better amongst the people who used the skin cream. You conclude that the skin cream is effective. We refer to this strategy as the ratio strategy. Among these 4 strategies, 2 of them leads to one answer, that the cream is effective. 2 of them leads to the other answer, that the skin cream is ineffective. But there is only one correct answer, and one logical correct strategy to reason with this question, which is the ratio strategy. But do note that the incorrect larger strategy also leads to the correct answer. So what we are seeing here is that to evaluate whether people can solve the problem correctly, we shouldn't only look at the outcome of the final answer. Visualization changes not only the outcome of the decisions people make, but also how they reason with data. We should closely examine the specific strategy people used to reason. Among the participants we surveyed, 25% of them used the ratio strategy, 10% used the delta strategy, 33% used the larger strategy, and 33% used the biggest strategy. The incorrect larger and biggest strategy are the most afforded by this bar chart design when participants reasoned to solve this problem. Just a quick note that not everyone who used the ratio strategy got the final answer right, because math is difficult. About 21% of them got the question correct. We can all agree that this low accuracy isn't great, so how might we help people more effectively reason with this? Existing work has demonstrated that presenting the same data in a different way might help people take a different perspective. So we tried presenting participants the same information using a table. Here's the big version of it. Let's try to answer this again. Is the skin cream an effective treatment for rashes? We observed the same 4 strategies participants reasoned with to solve this problem. The ratio strategy, where they compared relative ratios between patients whose rash got worse to better. The delta strategy, and that's almost like the ratio strategy, but the participants took the difference between the 2 sets of values rather than their ratios. The larger strategy, where participants compared only 2 numbers. And the biggest strategy, where the participants focused on the biggest number. Here is the distribution of participants who employed each of these strategies to solve the problem when it was presented to them in the table format. About 45% of the participants provided a correct final answer. We can compare the distribution of strategies for when participants saw the data presented as a table to when participants saw the data presented as a bar chart. And we see that they are quite different. This suggests that visualization design can change how people reason with data. The ratio strategy becomes much more prevalent amongst participants who saw the problem presented as a table. Specifically, people who viewed tables were approximately 2 times more likely to use the correct ratio strategy than people who viewed bar charts. This leads to an increase in overall accuracy to find the correct answer. Referencing existing literature in cognitive psychology, we see that it is possible that the mere presence of numerical labels triggers people to compute ratios. For example, people are more familiar with performing calculations on a series of numbers, and tables may be more associated with the type of strategic arithmetic practiced in school. Visual displays may be more typically used to perceive packaged insights and be less associated with the work needed to calculate insights. Future work can further test the effect of the presence of numbers in a bar chart on people's reasoning strategies, which may lead to guidelines pointing to the potential benefits of labeling values in bar charts. We also see that amongst everyone who used the ratio strategy, the participants who saw the table version were actually less likely to get it correct. This might bring a sigh of relief to everyone who is a visualization researcher like me. This suggests that visualizing the data in a bar chart is not all bad. While it is possible that the people who use the ratio strategy when reading bar charts might be better mathematicians to begin with, it is also possible that visual representations such as bar length can help people compare ratios more effectively than tables. Future work should look further into how we might leverage the strength of both representations to optimize reasoning strategies with data. Last but not least, the larger and biggest strategies were a lot more popular in bar charts. This corroborates with existing work, which demonstrates that people tend to make superlative comparisons, noticing that one bar is the biggest amongst a set, or identify the maximum and minimum values when bars are horizontally presented like this in an overlaid fashion. Future work can examine how other spatial arrangements might change how people reason with bar charts and potentially discover new strategies. I have one last thought to share with everyone. Why might we care about this? This example about skin cream seemed trivial enough, as most people are not invested to have strong opinions on whether the skin cream will be effective or not. But what if the topic was more belief triggering? Perhaps so belief triggering that it creates opportunities for cognitive biases that interfere with data-driven decision-making. What if the topic was about the effectiveness of a legislation on reducing crimes? To demonstrate the potential effects, we conducted a second study to be about the effect of a legislation on crimes in the city. The legislation calls for a ban on carrying concealed handguns in the public for several cities in a state. Here's the data showing the number of cities that observed an increase versus decrease in crime after concealed handguns have been banned. to be compared with cities that chose not to ban concealed handguns. Now, despite having thought the question through in a different context with the same numbers, it's still not easy, is it? Does it get easier if I show you the table version instead? We again looked into the strategies people used to solve this problem in this new context. We identified the same 4 strategies as in the skin cream context. And we can see the replicated effects here. Our participants were more likely to use the more difficult, but more accurate reasoning strategy when solving this problem with a table compared to a bar chart. The table representation more readily affords the ratio reasoning strategy. The data depicted in this example about guns and the effectiveness of a concealed weapon ban legislation is a strongly belief-triggering topic. So, in addition to relying on reasoning strategies, people might also rely on their prior belief to decide whether or not they disagree that the concealed handgun ban was effective or not. And it turns out, people do rely on their prior belief when answering this question. So the data-driven answer for this is that the ban is effective in reducing crimes. In addition to categorizing participants' response as correct or incorrect, we also noted whether the answer is congruent or incongruent with their belief on the effect of concealed handgun ban on reducing crimes. We refer to a participant as congruent if their belief is aligned with the data-driven answer. In this case, if they believe that banning concealed handguns is effective for reducing crimes. And congruent otherwise. Note that we have counterbalanced the data-driven answer to be effective or ineffective, and we captured the congruency of their stance by asking about participants' beliefs at the very end of the experiment. We can plot the number of people who responded correctly by the congruency of their belief to the correct answer, with neutral in the middle. If we plot the number of people who responded correctly, we see that participants were much more likely to answer the question correctly when their belief is aligned with the answer. This suggests that they might not be relying on reasoning to answer the question, but rather their own beliefs. Cognitive scientists refer to this tendency to rely on your existing beliefs to make a decision as confirmation bias. And we see that when the problem is presented as a bar chart, the tendency for confirmation bias is strong. And this pattern is much less strong for tables. Not only participants were more likely to use the optimal ratio reasoning strategy when solving the problem when it's presented as a table, they were also less likely to show confirmation bias. In conclusion, we should care about how people reason. Presenting people a problem in the right format, such as the table in our study, can not only help people more likely to use the correct ratio reasoning strategy, but also mitigate confirmation bias should the topic be a strongly belief-triggering one. While we found the table condition to be the right format to present our particular problem on skin cream effectiveness, we have yet to explore the degree to which this generalizes. So rather than strictly enforcing table usage or calling for a community-wide ban on bar charts, the takeaway of our work is as follows. When we create visualizations to help people solve problems and make decisions, think about the reasoning affordances of a visualization. Pick the data displays that best afford the right strategy. Thank you.